Hello everyone. So this is our last video on our liquid vapor equilibrium, and today in this video we're going to take a look at liquid vapor lever rule, that is the part of liquid vapor equilibrium. Okay, so in the first video we derived our phase diagram for our bubble and dew temperatures, right? And this is our liquid and vapor phase. This is going to be our pressure. And on the x-axis of our phase diagram, we had the mole fraction of a more volatile compound. And so our phase diagram looked something like this, with the top one with the bubble pressure and the bottom one with the dew pressure. Okay, so we're going to have specify one point here, right? And it's going to be our y1, which is the mole fraction of components in vapor phase. And here at specific pressure, that's going to be our x1, right? And here's something there is going to be our z1 value, which is the mole fraction of components in our mixture. So for example, in our specific case, we had a mixture of benzene and toluene, and Z represented the mole fraction of a more volatile compound. And we said that our feed is going to be equal to volume, not the volume, sorry, but the amount of compound in vapor phase plus the amount of compound in liquid phase, right? And we had another equation, which was a specific equation for a compound. So we multiplied this, the top equation, with the mole fractions, right? X1. Yeah, so we multiplied every phases with its mole fractions, so we got our equation that is specific for a compound. And now we can change our feed with V plus L and see what happens. So we can manipulate with this equation and see if there is any relationship between the amount of compound in the vapor phase and liquid phase. So if I open the brackets, it's going to be VZ1 plus LZ1 VY1 plus LX1. And I can get everything that's connected with the vapor and amount of compound in vapor phase to one side, and everything that is connected to the amount of compound in liquid phase to one side of our equation. So we can have our V as y1 minus z1, and I'm going to factorize it. And so for this one, it's z1 minus x1, right? And now we can represent their fraction, their ratio, so the amount of compound in vapor phase over the amount of compound in liquid phase, as z1 minus x1 over y1 minus z1. Yeah, so now we have our Lever's rule equation. So why is that so useful? So now if we take a look at our phase diagram, this line here represents y1 minus z1, right? So it's going to be y1 minus z1. And this line here, this distance, represents z1 minus x1. So we have both of them here. So the ratio between these two distances is equal to the ratio of the amount of compound in vapor phase and amount of compound in liquid phase. So when we had no computers, like no Python to calculate this stuff, people used graphing papers and actually measured the distance to have an idea of Lever's rule. So it was very useful tool back in the past. And What we can also see with this equation is, so let's have another phase diagram with bubble and dew pressures. This is P, and let's have for this part, let's say we have for the x-axis we have the mole fraction of a compound, and as the pressure increases we're going to hit a point where it is in vapor phase, right? And that specific pressure, it's going to have some amount. So if we say this is going to be y1, this is going to be x1, right? So at the same pressure, it's going to have some amount of compound in liquid state. And as we increase it, it's going to have y1 here and corresponding x1 here. You see, so as we're increasing the yi, we are also increasing the amount of compound in the liquid phase. So as we go until here, when it hits where it doesn't have any compound in liquid phase. So this kind of diagram, the phase diagrams, are very useful to represent how the mole fractions are changing, and that's the main idea behind the Lever's rule. So this was our last video regarding to the vapor liquid equilibrium, and I think it was helpful. Thanks for your attention.